We are doing roots and polynomials, part 2. So, just to recall from part 1 that we said to find the complex roots of a complex numbers, we will always use this formula. So, we always need to solve for r, and we also need to always solve for theta. So, basically the modulus and the argument. Just to recap, when we do roots and polynomials, a is our complex number. So if we find the nth root of that complex number, it is very important to write down the complex number for yourself so you can see which quadrant you're working in to be able to find r and theta. The nth root, that will be your value of n. That is one way they can ask the question. They can straight away just ask to find the fifth roots, for instance, of a complex number. Another way they can ask it is just to factorize or to solve. So factorize z to the 4 minus 4 or solve. Either way, you will always find the roots. So just remember, when we factorize, we will take the 4 across and we will find the fourth root of that number. Another way they can ask roots, they will just say solve the equation. So that is similar to asking to factorize. But either way, we will always find the roots. Now sometimes we need to complete the square or do the quadratic formula first before we can find the roots. What I mean by that, so say for instance you get an equation like this that we have said before, you cannot factorize. So you will do the formula plus or minus b, minus b plus or minus square root b squared minus 4ac over 2a, and we will continue from there. Now just something to remember here that is very useful. When you get higher, the order is higher than 2, which will happen a lot. Remember, especially when you get to the power of 4, this is squared, then you can factorize first. So you will have z squared and z squared. Since z squared times z squared is z to the 4, just like you did in school, which two numbers, when you multiply them, will give you minus 6, but when you add, will give you 1. So we know we have plus 3 and minus 2. Now, from this step, to factorize these two, what I said in the earlier steps, you will do the square root of negative 3, and you will do the square root of 2 using the square root of negative 2. The best is to use roots, and that's what we're going to do now. If we have to the power of 6 and we have a 3 here, we do the same. So we will have z3 and z3. So just remember it is 3 here. So we will do the same. Which two numbers, when we multiply them, will give us 4, but when we'll add it, give us 4. So we'll have 2 and 2. And then to get the roots or the other factors, we will just use our root theorem. So on that note, let's do this example. So very important, this example, factorize z to the 6 plus 4z cubed plus 8, and then write it in quadratic factors. So what we will do first, we will start by factorizing that equation. So what I've said just now, you see it is z to the 6 and z to the 3, so you'll have your two factors. If you struggle to see it straight away, like I did here, you can always use substitution. Most of you are familiar with K substitution from school, so if we let W be z to the 3, so we will always let K or W be the smaller factor. So if we substitute W equals z cubed into here, we will get w squared plus 4w plus 8. And what I've just said, so you cannot just straight factorize, you will use the quadratic formula. Just to recall what I said in my video for roots and polynomials, video 1, how do you see if you have complex roots? Remember from first year, if you get b squared minus 4ac is a negative number, you know you have complex roots. That is very useful, and I see that is not something students use often, but it is useful here, as in my example, I see that our b squared 16 minus 4, a is 1, c is 8, so I get negative 16, and I'm sure that I'm doing complex roots. So here I did the formula, minus b plus or minus b squared minus 4ac, square rooted over 2a. So please just make sure that you put the quadratic formula under all your theory when you summarize your theory, and you study it before you start with your examples. So when I simplify this, I get minus 2 plus minus 2i. So just make sure you get those steps. But remember now, my w is equal to that. What did I say earlier? I said let w be z squared, or z cubed. So in other words, I have now w, which is z cubed, is minus 2 plus or minus 2i. Remember I said earlier, so you are going to get the cube roots of this. So what I am going to do, since I have plus and minus, I will first find the cube roots of minus 2 plus 2i. So from what I've said earlier, very important, your insight is your complex root, which is extremely important. A common mistake students make. For some reason, they're not sure which cube root they must find. So it's always the cube root of the inside. So we know we're doing roots and polynomials, hence we're going to use our very important formula, which you should be familiar with that by now. We're doing cube roots, hence n is 3, and we have 3 cubed roots, so k is from 0 to 2. Now, just recall in the previous video, so this part is actually just revision of the first video. So I have minus 2 plus 2i. Since my x is negative and my y is positive, I am working in the second quadrant, quadrant 2. So here I have my r, and there I have my theta, and you see that theta is an obtuse angle. Obtuse angle, Hope you know that from school or first year. Obtuse angle in the second quadrant is between 90, it's between 90 and pi. So let's recap. So to find my modulus is r. I will just say real part squared plus imaginary squared, and I get root 8. And just recall what I said in the first video, we do not have to write it to root 2 because we're in any case going to simplify later. And then for my reference angle, just recall my reference angle must be my acute angle, and therefore I always use the positives. So that helps a lot. It helps a lot to remember acute angle, first quadrant, so x and y will be positive. I get arctan of 1, which is pi over 4, and I hope all of you by now is familiar with your special angles. So we will use special angles quite a lot, and just recall from the first video that for now I prefer to do the triangles. So I have 60 degrees here, I have 30 here, 1, 2, root 3, and then I have my 45 degree triangle, I have 45, 1, 1, root 2. Hence arctan of 1 is pi over 4. So by now you should know your special angles off by heart. But remember now what I said, we are working in quadrant 2. Hence we will have for our theta pi minus pi over 4, which is 3 pi over 4, our obtuse angle. So now we are ready to start with our formula for roots. So I have my r, which is root 8 to the power of 1 over 3. Here I have my theta, and here I have my n. I've just substituted everything into my very important formula, which you should know by now. Remember in maths, before you start doing examples, it is advisable to first study your theory before you start with examples. It just makes the process much easier. Now I have my very important formula for my 3 roots. Therefore, it's very important to write k is going to be 0, 1, and 2. So I have, when I simplify 3 pi over 4 over 3, I get pi over 4. So I get I pi over 4, and here this fraction will be equal to that. So now let's start and just do these quick. If I substitute k with 0, that is going to be for my first root. K is 0. I will just, so k here will be 0. So I just get root 2 e to the I pi over 4. And recall, e to the I pi over 4 is cos pi over 4 plus I sine pi over 4. Also Euler's formula that you are very familiar with at the moment. The next thing that is very important, cos pi over 4 and sine pi over 4 are both equal to 1 over root 2. And then when I simplify that, I get 1 plus I. So now just recall from our previous video, if my equation has real coefficients, that includes my constant term. The roots will be in conjugate pairs. So if I had something like that, since my coefficient is 1 and my constant is -1 and they are real, my roots will be in complex conjugate pairs. But be careful, what are we doing here? What are we doing here? We are finding the cube root of -2 plus 2i. In other words, we are doing this, plus or minus 2i, where the constant is not real. Hence, the roots will not be in conjugate pairs. I cannot assume right away that my other root will be 1 minus I. So just make sure of that common pitfall from students. Now I do z equals 1. Z equals 1. So if z1 I mean, so if k is 1, this is what I'm getting, substituting into my very important formula. So, when I get this, so remember from school, when the bases are the same and I'm multiplying, I add the exponent. Hence, this will be my root. Now, a very important fact, just remember that 11 pi over 12 is not a special angle, so I cannot simplify that. But something I want you to remember that is very important, your angle need to be between pi and negative pi. How do we check if 11 pi over 12 is in that range? Now, a trick I teach my students, so all you say, what is the closest number to 11 that's divisible by 12? So you know 11 pi is 12 pi minus pi over 12. And in maths, if we just have one factor in the denominator, we can split. So what do I get here? Pi minus pi over 12, which is smaller than pi, so it must be in this range. So I am fine with that value. Now my third root will be when k is 2. I replace 2 in my very important formula and I get this root. Just remember again, my bases are the same. I add my exponents and this is what I'm getting. Now, what is very important, I want to know if 19 pi over 12 is in this range. So, just look what I do again. I say, what is the closest number to 19 that's divisible by 12? Say I have 24 minus 5 pi is 19 pi over 12. I split, so I have 2 pi minus 5 pi over 12. So I am here. So now, if you want to see if you have negative 5 pi over 12, you want to know if it is in this range. If it is in this range, and yes, it is, because minus 5 pi over 12 is just in between there. So you are fine with the minus 5 pi over 12. Just remember, why is it minus? Because 5 pi over 12 will be on this side. This is 2 pi minus, so if I'm here, I know that is negative 5 pi over 12. Very important. So I have my 3 roots from k equals 0, k equals 1, and k equals 2, which should be very clear by now. But remember, I'm finding the 6 roots of z to the 6 plus 4z cubed plus 8 equals 0. Now, very important, I hope you can all see that my coefficients plus my constant are all real values. My coefficients and my constant are all real values. They are all real values, very important. So, polynomial which has real coefficients including the constant term will have, if it has complex roots, they will be in conjugate pairs. So, let's go back to our roots. What is, so I just want to rectify here. So remember, we had the root 2 as the r also. So let's just put them in here where the roots are. So don't forget the r, like I almost did now. So root 2, root 2, root 2. So because I just want to see if you remember, if you have e to the I theta, or e to the I theta, immediately, what is the complex conjugate of that? It is r to the, or e to the I, negative I theta. Very important. That's why my conjugate of this root will be minus I over 4, hence the 2 roots here. My conjugate of root 2e to the 11 pi over 12 will be negative, hence plus minus. Then the same for my last one, hence the plus minus. And there I have my 6 roots. Beautiful. So now, very important, always in maths, end off with what they were asking. Remember, they were saying factorize into quadratic factors with real coefficient. Coefficients also include constant. So, what is our problem here? Our problem is that we have the conjugate, the I is the problem. So we want to get rid of that. Just one thing, I just want you to be familiar with a sketch. If I sketch these two, pi over 4 is 45 degrees. There's my pi over 4. There's my root 2, my radius. So that root will be over there. Its conjugate is symmetrical to the other side. Very important, the root 2 stays the same. But just note, I've changed my angle. Now, if I sketch this one, remember what I did earlier. I said 11 pi over 12 is 12 pi minus pi over 12, which is pi minus pi over 12. And from school, you know that second quadrant. It is just maybe useful to remember that pi over 12 is 15 degrees. It's just very useful in maths, even though you're not allowed to use degrees in a test, just to remember roughly. Why am I saying that? Because then you know it's very close here, because here we have 15 degrees. And then the conjugate will just be symmetrical to the other side. So there I have those 4 roots already. And then remember what we've just done now. We had the negative 5 pi I over 12 which is the red here. So 5 pi I over 12, let me just do them here. 5 pi over 12. So if you want to see 5 pi over 12 pi over 4, which one is smaller, which one is bigger, it's a trick actually from grade 9 where we get the denominator the same. So here we get 5 pi. Here I want to get denominator 3. So I have 3 pi over 12. So 5 pi over 12 is actually bigger than pi over 4. So what do I see? So it will be there. So for instance, but still root 2. The conjugate here, but still root 2. And just note a very important point and also a common mistake students make. They don't realize that it will be a circle with radius root 2. Mine looks now more like an ellipse, but you will always get a circle. So the roots will all fall on the same circle. Why? Because your radius will stay constant at root 2. Now, just something I want to mention, also a common pitfall that students make. It is not wrong, but it's just very useful for later. So when we are given that a plus bi is a root, and we know that the conjugate is also a root, and they ask us to find the polynomial or the factors. Now, very important, please make a note of what I'm doing now. If you take it across, you will get z minus a minus bi. On this side, if I take it across, I will get z minus I plus bi. So in other words, if I want to get the quadratic factor, I will get this. Now something that I want to show you that is going to be extremely important for later, you will make your own brackets over here. Why am I doing it? Can you all see that I have, for instance, those two are the same, so I have the conjugate there. And recall from a previous video, if we have c plus di times c minus di, I just go straight away c squared plus d squared. This is something that we use often to save time. Do not do difference of two squares. Just go straight. So what will I get here straight? Just z minus a squared plus b squared. And I can times that out, and this is what I will get. Very, very important for later. So I do advise you to take note of this for later. Take it to heart and please remember this. Very useful. So that brings us to what I want to say now. So here we have our 6 roots of, remember what our formula was, or our equation, z to the 6 plus 6z cubed plus 8 is 0. 4z cubed plus 8 is 0. And we now have these 6 roots. But remember the question was to find a quadratic equation with real roots. So We know now that we have root 2, if we look at our first one, root 2 plus or minus I pi over 4. Now remember earlier I just got z is 1 plus I, but because they conjugate plus or minus, I know 1 minus I is also a root. Now I'm going to use this technique. Very, very important. Look what I'm doing. I'm taking the 1 plus I across. I'm taking the 1 minus I across. I make my own bracket so that I have conjugates. So I have z minus 1 squared plus 1. And when I times it out, this is what I'm getting. Was it a linear factor? Linear factor with real coefficients. Can you all see? No complex numbers, no i's included. Why linear? Because I have my z squared minus 2z plus 2. So now we will do for root 2 e to the plus or minus 11 pi I over 12. So here I'm doing the positive, here I'm doing the negative. So just recall, very important, you know that by now we use it all the time. This is cos theta plus I sine theta. And please, what I'm stressing, please do not, while you're doing examples, refer back to your theory. You should know it as well as I do at this moment. I'm not referring back to any theory. So you should first study your theory. So I've changed this in here. And negative I've changed in here. So please recall, please just recall that e to the negative I theta will be cos theta minus I sine theta minus plus. Two things that will come up a lot in any test. Now what I'm going to do, I just distributed the negative root 2 into both, and this is what I'm getting, all from greater 9. So I'm not wasting time on that. What I do stress is I see again these two brackets are the same. Here I have minus, here I have plus. So what is it? It's again this very important technique. So what do I get? I will always then get the red bracket squared. But what do I do with the conjugates? I just say b squared. So what is my b here? It's root 2 sine 11 pi over 12 squared. And root 2 squared is 2. So hence that. Now I distribute the red bracket out. This is what I'm getting. So I'm not going to spend time on that. When you do the video, just pause here and make sure you can multiply it out. Like I said, I'm not spending time on grade 9 to 12 work. All the things that you should know. Now what you should also know that 2's cos squared with the same angle as this angle sine squared will just give you 2. From now on, you're all familiar with the fact that sine squared plus cos squared with the same root, the same angle, will always give you 1. What did I end up getting? There is my quadratic factor. What do I see? No i's included, so only real coefficients. Now, for the last root, remember we've done it now for these two. For this one, I will just leave it up to you to do. It's exactly what I've just done. Exactly what I've just done. So you can see for yourself if you understand it, and just do it exactly the same as what I've done with these two. So that's good practice. Now, let's go to our final example for roots and polynomials. In this video, they will ask us to find the complex partial fractions of 16 over z4 minus 1. So just to recap, in the beginning, I did the summary, because common pitfall when students see this factor, they try to immediately just do z squared minus 2, z squared plus 2. Not wrong, but it is normally then students are not very accurate. What did I say? You will always find your roots. So we did these roots in video 1, but let's just recap quickly. So remember what I said, even though you're factorizing, you are going to get the roots. Using what? Using our very important formula. And now for k equals 0, 1, 2, and 3, because there are 4 roots, and n is 4, since we are finding the 4th root. So let's go quickly. We sketch. So now remember what I said earlier. Your complex, you're finding the 4th root of 1. You're finding the 4th root of 1. Remember I said a common pitfall, students do not take the inside. Now where do I sketch 1? Remember from the previous video, it's just on the positive x-axis. On the positive x-axis, I know the radius will be 1 and my theta will be 0. So to find the roots, I'm going to substitute theta back in, and I'm going to substitute my r back in. What do I get? I get 1 to the power 4. I get e I theta, which is now 0 over 4, and I get 2k pi I over 4. So what do I get? 1 to the power of anything is 1. Also a common pitfall from students, they don't know something as easy as that. E to the 0 is 1, so I just have k pi I over 2, but k is 0, so k is 0, so I just get 1. My first root is 1. My second root, k is 1, so I get pi I over 2. Now, very important, I even pasted it here. Remember what we said. E to the I pi over 2 is I, negative I pi over 2, negative I. So I do suggest you study these very well before you start, because remember they come up everywhere. So this one will be I. Here I will have this again. It is 2 now, so I'll get pi I. So can you see I'm using this again, pi I, which is negative 1. Negative 1, and then my last one is it's 3, so it is, k is 3 now, so I have 3 pi I over 2. So this one you can actually see cos f 3 pi over 2 plus I sine 3 pi over 2. 3 pi over 2 is 270. Cos of 270 is, if you do cos of 270, you know that cos of 270 is 0. Sine of 270, if you do the sine graph, sine of 270 is -1, so you get negative I. Just note that, so lots of things to remember, but just note that your coefficients of your polynomial are all real, so the roots are in conjugate pairs. You could have seen it immediately. I just wanted to run through it quickly just to make sure. Now I'm going to express as partial fractions. So just remember what I've said earlier. You have z equals 1, so you have your factor z minus 1. Then you have z equals -1, so you have z plus 1. You have z equals I, so you have z minus I, and here the last one you have z plus I. Hence my partial fractions. And because these factors that I'm doing in blue in the denominators are all linear to the power of 1, my numerators will just all be constants. So that is partial fractions. If you're not familiar with partial fractions, please study it first, as I'm not going to go here into the details since it is first year work. Now, the next thing is if I times by the common denominator, so my common denominator will be those four factors. So what I will get here, I will get my 4. So let me just write it in here, because I want to get my LCD the same. So z minus 1, I have to times by z plus 1, z squared plus 1. Where is the z squared plus 1 coming from? Because I times by z minus 1, z minus I, z plus I, that is z squared plus 1. Again, that quick method. And then I times b by z minus 1 and z squared plus 1. And then my z minus I, so I times it by z plus I, z squared minus 1, and then my d. So this is all partial fractions. Please revise partial fractions. Now my denominators are the same, so I can equate my numerators. Now the best is to use this method. If z is 1, why am I using z equals 1? Because this factor will disappear. Why? Because 1 minus 1 is 0. So I'm looking for values that will make other three factors disappear. Z squared minus 1, z plus I, z is 1, this factor will disappear. And then our last one is d, z squared minus 1, z minus I. If z is 1, this factor will disappear. So what do I have left? I just have a z plus 1, z squared plus 1 equals 4 left. If I substitute z equals 1 in, I will get 2 times 2a is 4, and hence a is 1, what I'm going to use later in my partial fractions. Now we can actually do b first. So what can I make? If I make z -1, So let's look at this one. If I make z negative 1, which factors will disappear? Obviously this one, minus 1 plus 1 is 0. Here, 1 squared minus 1 is 0. 1 squared minus 1 squared minus 1 is 0. So I only have my b, z minus 1, z squared plus 1 left equal 4. So just note, if I substitute z equals negative 1 in here, the factor will not disappear. I will get negative 2 times 2 is 4. So I will get b is negative 1. So what do I have so far? I have b is negative 1 and I have a is 1. Now I need to get c and d. So let's see. If I use z equals I, let's see if I use z equals I. Let's see which factors will disappear. So I squared is negative 1. This factor will disappear. The same here will disappear. And I minus I is 0. This one will disappear. What do I have left? I just have cz squared minus 1 times z plus I equal to 4 left. If I substitute I in, I squared is minus 1, so I get minus 2. And here I'll get 2i is 4. So I'll get ci is negative 1. But remember, 1 over I is negative I. So that means that c is I. So that's all from your basics. And then you do d exactly the same when you make z is negative 1, you can check that by yourself and you'll get negative I. So there you have your factors. A is 1, so that's where I've substituted that. B, let's see, B was negative 1. C was I and D was negative I. And there you have your partial fractions. So in maths, it is very useful to break a complicated factor in the denominator if your factor in denominator is complicated, to change that fraction into partial fractions. Why? Because, for instance, when we integrate, then we will make it easier now that we have split it. So I hope you understand that. If you're not 100% sure of the partial fractions, please make sure you study that first from first year, because now we've just applied in complex numbers. So here I've just pasted again the theory that is extremely important. And you know by now the i's roots are very, very important. So I hope you understand this video 2 of roots and polynomials. So if you do both videos, you should have a full understanding of roots and polynomials. So for any questions about this video or upcoming videos, you are welcome to email me on drbrooks@universitymaths.co.za. And that is the end of roots and polynomials.